So I am thrilled today to introduce Ollie, Professor Ollie de Weck. He told me to keep it short, so I've got to try and figure out what I can trim quickly on the fly here. His background is industrial engineering and aerospace engineering here at MIT. He spent some time in industry before coming here to MIT as a faculty member and time in the aircraft program at McDonnell Douglas. And I think that does bring in a little bit of background to what you're talking about today with your time in the aerospace world. Professor de Weck's a leader in systems engineering. He focuses on complex man-made systems such as aircraft, spacecraft, automobiles, printers, and critical infrastructures, and how they're designed over and evolve over time. His emphasis is on strategic properties that have the potential to maximize life cycle, the ilities. And I think any of you that have been through Ollie in the core have learned on the ilities. Since 2001, the group has developed quantitative methods to consider manufacturability, flexibility, commonality, and sustainability, among other characteristics. From 2008 to 2011, he was the associate head of the engineering systems division here at MIT. He's a faculty director for the MIT Gordon Engineering Leadership Program, faculty co-director for the UPOP, the Undergraduate Practice Opportunities Program, and the faculty director for the MIT Switzerland program. But Ollie spent 2 years from 2016 to 2018 in industry. He was the senior vice president for technology planning and road mapping at Airbus. And he's taken his research and experience at Airbus and currently teaches one of the more popular STM electives in technology road mapping. And I welcome Ollie today to talk more about his insight on this topic. So thank you.
Thanks, Joan. That's awesome. Thank you so much. It's really great to see you all. Before I start, I want to say something to Lisa. My wife Lynn and I, we watched the documentary about Theranos last night, actually. And I think, Lisa, you are MIT's response to Elizabeth Holmes. So I want to start with, I'd like to start with this picture here and ask you, what does this show? Anybody? What's shown on this picture? Yes, it's it. Yes, yes, that's at the component level. And then, okay, but what system is this? Anybody know? It's the Deep Space Network, the DSN. This is the system that's used to communicate with essentially all of our interplanetary probes. Have any of you seen the recent pictures from Mars, from the rover Perseverance or the Ingenuity helicopter? All those signals travel through that system. It's managed by JPL. Why do I show you this? Because this graph here is really, when I first saw this graph, I couldn't stop staring at it. And still now, I can't stop staring at it 25 years later. How do we know that this graph is about 25 years old? Well, you see a solid line, and then it becomes a dashed line. You see that? If you go down here, you see, oh, that's about 94. So this is actual, and this was predicted. Kind of a roadmap, right? What does the graph actually show? The data rate in bits per second over time that was achievable with the Deep Space Network at a Jupiter equivalent distance, which is 750 million kilometers from Earth. So here's our spacecraft at Jupiter sending a signal, a digital signal back to Earth. So what this essentially is showing us is that our data rate, our ability to send data from Jupiter back to Earth has improved since 1960. This is logarithmic by 13 orders of magnitude. Not a factor of 13, 13 orders of magnitude, which is astounding. So this is, I think, for engineers, I see this as the equivalent of the famous Napoleon chart that many of you know about. You can look at this chart for half an hour and still learn new information. So one of the things I think we do well at MIT and other places well is understand why, how was 13 orders of magnitude achieved in 60 years? And it all comes back to the fundamentals, the fundamental physics, the fundamental chemistry, biology, economics of the situation. and governing equations. This is a governing equation known as the link budget equation. It essentially gives you the data rate, R, on the left side, as a function of its constituent factors or drivers. And this is the logarithmic form, which is nice because everything becomes sums and it's essentially a sum of factors. So how much power is in the signal? Shannon's limit. The space loss, can't do anything about that. That's the distance from Jupiter. But some of these other factors we can do a lot about. Transmission losses, antenna gains, system temperature, keeping the receiver really cold. And we can break it down into the second level and third level of decomposition. So the radiated power depends on gain, the transmitter gain, the power in the signal, and so forth. And every one of these terms has improved and contributed to that 13 orders of magnitude. And you can then break it down to the individual enabling technologies, the antennas, the transmitters, the coolers, but also the software, the waveforms, the error correction codes. All those technologies together at the top level of the deep space network have achieved together this incredible improvement. So technology road mapping really is about understanding that evolution historically, but forecasting it into the future and making choices as to, given a relationship like this one, which of these technologies are the most important, are the most promising, where we should put our efforts, also taking into account the absolute limits that are given by physics and the underlying sciences. So as Joan mentioned, I've been affiliated with SDM since 2001, which was really great. And I want to thank Ed and Tom, who both got me involved in this program in my very first year on the faculty here at MIT. And to be honest with you, initially, I wasn't sure I really should do this because it was kind of far away from my research. But every year that I've been privileged to teach in SDM and advise students, I've become more excited about it. But it's good to take a break once in a while. So in 2016, I was invited to join Airbus for 2 years. I took a leave from MIT. And the question was very similar to the DSN. What are the key technologies that Airbus should invest in for commercial aircraft, but also helicopters, satellites, and services to improve the position of the company and the industry in the future? One of the really exciting things that happened was this. In 2018, when I was there, the first flight of the new A350 ultra long range airplane. And I don't know, Tom, if you've flown on this. This is the very famous SQ-21 flight, and I just checked it. Yesterday, it flew from Newark to Singapore, 18 hours and 50 minutes. It's basically a 19 to 20 hour nonstop flight. So this flight was commercially offered before on an older airplane, the A340, but it wasn't economical. The business class did not close in an all business class configuration. The A350, however, is making it close because the efficiency of the airplane, the aerodynamics, the fuel burn is so much better than the older generation that now this really ultra long, it's the longest commercial flight in the world, actually is closing. And so I think what I want to show you here, don't worry, we're not going to go through this in detail, but my 2 years at Airbus were incredibly interesting and enriching. You can think of Airbus as like a mini European Union or even a mini UN, Germany, France, UK, Spain, right? A lot of different countries came together to create this company, now expanding into China, the US as well, and Canada. And to really make sense of all the different technologies, all the different products across the group, we developed this methodology here, which we call ATRA, Advanced Technology Roadmap Architecture. And I just want to point you to the center here. It's essentially 4 steps. Every year, with the annual budget cycle, we go through these 4 steps. Where are we today? Where could we go? Where should we go? And then where we are actually going. And you can notice on the right side, these outputs they're not just visuals, but they're very quantitative. Lisa, you mentioned this, unless you're willing to go and quantify, get data, run the numbers, and understand where you stand, where your competitors are, how the technologies are improving according to certain figures of merit. And here we bring in a little bit of Markowitz portfolio theory. Are you going for a pretty safe portfolio with more incremental improvements? Are you going for more higher risk, maybe higher payoff portfolio? That's fundamentally a management decision, but you want to show these non-dominated choices and you want to show how you arrive at them. That's essentially what it is. And I just want to show you with some pictures what that looked like in practice. So it took about 6 months at Airbus to figure out what's going on. It's a huge company, 130,000 people, 60 different locations in about 10 countries, and a very messy R&D portfolio. Exciting, but messy. So we did several workshops, and you see here, each of these sheets is a technology area. Some of them, there's a lot going on here. Some of them, you see in the documents and the discussion, oh, we have a very active program in artificial intelligence. But when you actually try to find the projects, there isn't much going on. So what's the truth here and what's the situational awareness? So where are we today? The other thing I want to say is this is a picture of the Airbus Leadership University. So Airbus decided that leadership, which remember was on the top of the pyramid, right, in the SDM architecture, leadership is important enough for us as a company, we're going to create our own university. It's in Toulouse, and it's a really cool place. So we used it extensively. It's actually circular, and there's a famous square in Toulouse called the Place Wilson, named after President Wilson. So the dimensions of this university match exactly Place Wilson in Toulouse. And it has fantastic facilities for doing this kind of work. It's very difficult to do technology road mapping and thinking about the future if you're really embedded in your day-to-day pressures, the phone is ringing, the emails are going. You need to be a way to really think quietly about the future. So we used the Leadership University a lot. So one of the things that came out of this work was this graph. And what does it show? Well, here's the different technologies. Each of them has its own roadmap. Interdependencies that we found, a lot of them, about 3,000. And so, for example, one technology is linked to another. Requirements are imposed. Figures of merit are shared, and so forth. I showed this graph at the executive committee of Airbus. And what do you think the reaction was? Almost, yes, the verbal equivalent of this. The CEO told me, Tom Enders at the time, why are you making it so complicated? Why are you making this so complicated? My response was, I'm not making it complicated. What we're doing here is we're revealing the real complexity in the company. We're showing you what's really going on. We're not adding complexity. We're making it transparent. But, fair point. So how can you act on this? Well, here's another method, DSM, right, Steve? Same links as you saw before, but now they're reorganized and they're grouped and clustered. And what we found is that, so here's your products, a lot of different products, but here are all these technology areas grouped now into 5 clusters. DDM, digital design and manufacturing, materials, autonomy, connectivity, electrification. And we decided that there should be a leader for each of these clusters of technologies, a VP level leader. There should be a budget, and it should be focused instead of diluting the effort. So those clusters became really a focal point. And just to show you a little bit what that meant in the end, meant funding projects. Some were already ongoing, so it's confirming this is a good direction. And some were new projects that we launched in each of these 5 clusters. For example, a lot of talk about decarbonization of aviation. Well, 2 megawatt class hybrid electric propulsion system. There's a building now in Munich called the E-Systems House, where a lot of these high power electric systems are being developed and tested. This is a rendering of the, it looks like a big quadcopter, right? This one carries people. This is the city Airbus, which had its first flight last year in 2021. Software-defined radio, conformal antenna arrays, the idea that if you look at a commercial aircraft today, it's got all these little radomes and antennas. Shouldn't the skin of the aircraft be the antenna? Well, it takes a lot of development, autonomy, airplanes and drones that can fly around the weather and replan their mission automatically or autonomously, single pilot operations, 3D manufacturing with metals, dry fiber, meaning composites that don't require an autoclave, which is always a bottleneck, model-based system engineering, big topic in SDM today, and then collaborative and reconfigurable robots, humans and robots working together on the assembly line. So come back to MIT. I've been back since 2019 and really, really happy. There was never a question that I would not come back to MIT. I was really happy to come back. And like Joan said, created a new class here called Technology Roadmapping and Development. And I think I'm actually going over the proofs of the book. It should come out May 1st right now. And Steve, you and I had breakfast, do you remember that, at Trieste? And this was the title that we talked about. So thanks for counseling me on that, Steve. Appreciate it. And the other thing that also we did is create a professional version of the course. So there's an SDM on-campus version, and there's also now an online version of this material through MIT Professional Education. And then finally, the last thing I want to mention is, the students, and about half the students taking this class are SDM students, create their own roadmaps, their own technology roadmaps using this approach. And if you go to this website, roadmaps.mit.edu, you'll see about 58 different technology roadmaps that were created over the last 3 years on many, many different topics: bioplastics, robotics in agriculture, blockchain, et cetera, et cetera. So it's been really, really fun to be back. It's been fun to come back from industry, bring some of the real challenges here. And I always keep being inspired by you guys, the students, the colleagues here. MIT is a great place, and I look forward to many years to come. So with that, thank you for your attention.